Hi, I'm Walter Grayman, representing the Environmental and Water Resources Institute, EWRI's WDSA History Project. The purpose of this project is to document the history of water distribution system analysis. An important part of this project is a series of interviews with engineers, modelers, researchers, and practitioners who have made significant contributions to the field of water distribution system analysis. Our interview today is with Dr. Tom Walski. Tom is a Bentley Fellow at Bentley Systems. He has been in the forefront of water distribution system modeling for the past 35 years. Over that period, he has worked in all facets of the industry: academia, consulting, research, and utilities, and has written innumerable papers and books. His knowledge of the field of water distribution system analysis has been felt by thousands of engineers who have taken in-depth classes from Tom and have used his books as their primary source of information. This interview is being conducted on May 17, 2015 in Austin, Texas. Tom, you've been active in the field for over 35 years. Can you remember the very first time that you ran a water distribution system model?
Well, the first actual study that I did, it wasn't just an example problem, was on the island of Guam. Did a regional planning study, and it is the first place where I really got to use some of the ideas I had about model calibration and the need to really crank up the flow so you have a lot of velocity, a lot of head loss, and that's how you can really test a water distribution system model. That was like early 1980s, because up until then there was no real standard for calibrating models, and of course there still isn't a good standard, and I think that's with good reason. But people would just take some static pressures and compare to static pressures, and if they're reasonable, they'd say, okay, our model's calibrated. And I guess that means you don't have gross errors, but to really find out pipe roughnesses and demands and those kind of influences, you really have to have head loss. And the head loss has to be greater than the error in measurement. And so that's where we spend a lot of time there, just refining those ideas and getting a model that was really believable. And you really learn a lot about a system when you calibrate it using high flows, because that's where any kind of errors and roughnesses or closed valves are really going to show up. And so this first study I did is really where I started to develop those ideas and do some more work on model calibration, which is one of my pet topics along the way. Getting good quality data to make sure the model really behaves like the real world, because that's what a model is supposed to do.
So have we gotten better in the last 30 years in calibrating models?
Yes, there's been a lot of stuff that's been done that have made the calibration process better. First of all, we're not skeletonizing models as much, so the model inherently starts off a little better. And people are realizing that they do need to do calibration tests. And you don't really see that many papers anymore about model calibration studies, because folks just realize it's part of developing a model. Now, occasionally you might hear someone building a model without calibrating, but that's kind of the exception to the rule. People know they're supposed to calibrate, and that calibrating during high velocity periods and getting good quality data are really important. And now with things like digital terrain models, we've sort of minimized the error in elevations, and with SCADA data we have a lot more data that we can use for calibration. So things have gradually gotten better, but still it boils down to garbage in, garbage out. You know, a lot of times nowadays when you see the model and the physical data diverging, a lot more times it's really the field data that's wrong. And the people are using the model to find out when they have bad sensors. It's gotten to that kind of point that the models are really getting very good. And if you do a good job with calibration, calibration will show you, well, this gauge doesn't look right.
A few years ago, we tried to develop a set of calibration guidelines, and it never really went anywhere in terms of general acceptance. Should we be trying to develop some fairly significant guidelines?
No. This is something that, one of the earlier papers was by Don Chase, where he put out some examples of how you might have some standards, and all of a sudden people grabbed onto them and started claiming that they were AWWA standards, and they never were, and Don never really intended them to be. They were just something that was out there. And the problem with this is that you can't just come up with rigid numbers that apply everywhere. Every system's different. Every system has different quality data, different uses of the model. If you're going to be using a model for water quality purposes, fire hydrant flow tests really aren't all that important. On the other hand, if you are using it for fire flows, fire hydrant flow tests are extremely important. So you just can't come up with a standard that says, thou shalt calibrate it, calculates, let's say, 20 fire hydrant flow tests per every 10,000 nodes or something like that. You just can't come up with it because it depends on how many pressure zones you have, how complicated the network is, and how willing the owner is to spend money to get the data, because this effort isn't cheap. And so that's why the rule that we kind of use is that you have a calibrated model when the cost of doing more calibration exceeds the benefits. And that's really the rule. And anytime you try to get more codified than that, I don't think you're going to be able to come up with anything more general than that.
So one size doesn't fit all, and we have to be really dependent on modelers being understanding what's needed in the way of calibrating and essentially pushing that the utility or the user is going to follow the calibration.
Yes, the most important tool for model calibration is between the modeler's ears.
Let's step back now.
Okay.
You've had a long career, still going on. You've worked for a variety of institutions with much of your emphasis in the water distribution system modeling field. For organizational purposes, I'm going to question you following your career chronologically. In the 1970s to 1980s, you worked at the Corps of Engineers Waterways Experimental Station in Vicksburg. Some of your accomplishments during that period included the development of the WDSA modeling software, extensive field work in analyzing water distribution systems, and publication of your first book, Analysis of Water Distribution Systems. Can you tell us a little bit about these accomplishments and others during that period of your career?
Okay, that's about 4 questions now that I've heard them. First of all, I think one of the things the Corps drilled into us that you don't see at other places is that research should have some practical benefits. You couldn't just do research in the Corps of Engineers because it was a neat idea and no one did it before, let's try it. You had to be able to justify that if we do this research, these are the benefits that are going to come out of it. And I think the Corps held us to a higher standard than most people are held as far as your research work had to have some kind of practical benefit. And so that kind of drilled it into me that research for research's sake might be okay to a certain extent, but you really needed to be able to have some vision of how this is going to be used. Okay, so that's the first part. Some of the work we did on the WDSA model with Johannes Gessler and John Schustrom was really good. Johannes already had a good solver that he developed himself, and we converted it to Fortran and made it very user-friendly for that time period. Now it looked pretty bad by today's standards, but at the time that was really good. And one of the things that we wanted to do was look at multi-objective optimization, because no one had done this in water distribution systems. There had been some talk about it, and some of the early stuff by guys like the MIT group back in the 60s talked about it if you read some of the early papers, but nobody was really trying to quantify it. And we really had the first program that did that. Now, since then, the state of the art is everybody is trying to do multi-objective water system optimization, and the more people try to do it, the less enamored about it I am, because it's so hard to figure out the other objectives. We have cost is an easy one, relatively speaking. If you do a good job with it, it's not. But let's say cost we can quantify. On the other hand, some of these other parameters that people try to use as surrogates for reliability or capacity are not really all that good. And I'm still struggling with coming up with the ultimate other objectives. There's one paper a year ago or so that won an award that had like 7 objectives. And basically the result of that was that if you said, what should I do? The answer is, I don't know. Because there are just so many objectives and so many ways of looking at it, there was not a definitive answer to it. So I'm not sure we've got that ability to apply it, multi-objective optimization, or even optimization in general. And the other thing about the optimization is almost all the programs essentially look at a fixed time horizon. They have some known demand, and a known demand doesn't really exist. There's huge uncertainty. So what you're doing is optimizing, assuming that you have a perfect demand forecast at some point in time, which you don't have. One of the things that's certain about demand forecasts is that they're all wrong. So optimizing, they may claim to save $8 million if you ran this optimization, but if you have the slightest error in your demand forecast, it may cost them $12 million to save $8 million. So I'm not completely convinced of optimization really being the ultimate solution. I think it's, again, the engineering judgment and ability to account for uncertainty in forecast and uncertainty in the future, because we really don't know what the future brings us.
On a personal note, back in 1984, when I was doing some work with EPA, and we were looking at water quality modeling, Tom, you were working for the Corps of Engineers, and you came out and did some field testing for us, and fire flow testing using parallel hose method. For me, it was a real eye opener, and especially to see this PhD out in the rain testing systems.
Yes, you got to do it. You can't calibrate a model sitting in an office. You have to go out and get data and also interact with the operators. There's a lot of the information that they have in their heads, and you've got to extract that. I think that's one of the lessons that Maurice Maslia learned in his studies when he was doing Tom's River and Camp Lejeune, that there's just so much detective work. And that's one of the papers I did when I was in Austin, was about, is model calibration more about Sherlock Holmes or Hardy Cross? And it really has more to do with Sherlock Holmes, digging up the data, and you can't do that sitting behind your desk, even though it's a lot easier to sit behind your desk and make assumptions. If you really want to get things right, you've got to go out there and physically look at things and measure things and understand the error in measurements that you're collecting, and the data you're collecting.
One of the events that some of the old-timers, a lot of the old-timers remember, was in 1985, where you organized the Battle of the Network Models session at the ASCE Water Resources Planning and Management Conference in Buffalo. In this session, participants used alternative models or methods to determine the optimal sizing of pipes in a hypothetical water system. Can you tell us a little bit about that and kind of talk about it's now 30 years later, and has the field of optimization as applied to this area, has it progressed in the manner that you thought it would back in 1985?
No, it kind of proved me wrong, I think, the field. What happened, I remember at the summation of the session, I said that, well, in a couple of years, everybody's going to be using optimization to help design their system. And that was one of the many errors I've made in my career, because people now, 30 years later, optimization is still kind of a fringe tool, because as soon as you start using it, you start to realize the shortcomings, as I talked about in the earlier question, and so it hasn't really caught on in engineering practice. While modeling itself has become very much part of the DNA of anybody designing a system, optimization hasn't. I think there's a story along the lines of, optimization is the wave of the future, and it always will be.
From 1987 to 1992, and then later from 1997 to 2000, you worked at water and wastewater utilities, first in Austin, and later in a few places in Pennsylvania. Please talk about your experiences during those periods in terms of the water distribution system area.
Yes, it was a great learning experience, because you can, with the Corps of Engineers, I was still not the inside guy. I was somebody who came from out the research lab and went out to help out with studies at Army bases or regional studies, and I wasn't on the owner's side. And things look a lot different from that side. So when I went to Austin, Texas, I was finally on the side of the people who really made the decisions and controlled things. And I learned so much about the decision-making process, how it doesn't really fit minimize f of x subject to g of x. It's really very different than I thought it was before I got into the actual side of making these pipe size decisions. I'd make recommendations in the past, but here we were actually making decisions as to what projects to build, how big they were, when to build them, and it really helped me to put the ideas that I had from my Corps of Engineer days into practice. And I learned a lot about misconceptions I had, and it's something that I would encourage people to do before they started research, is to actually work for utility for a few years, and you get so much better, a different perspective on it. And in Austin, we really did some interesting things. It doesn't mean I was outside of research. One of the interesting problems I worked on there was Cat Mountain Cove. We're in Austin now, and this was a high spot in the system where the people were complaining that they'd run out of water every once in a while for about a minute or two. And I ran our model, and obviously they're getting 40 psi or so they're wrong. Well, my boss said that she didn't really care what my model says. I was going to fix the damn problem, and that was it. So we put out pressure gauges. Teresa Lutz, who's now the head of system planning here, and I put out pressure gauges and recorded it. And sure enough, there were periods of time where the pressure would just drop to zero. And we did some calculations, and it turns out it was transient problems when they turned off a certain set of pumps. And this was really the first publication that we did that showed that you could have negative transients under normal operation conditions. And since then, there's been a lot of research work. People like Marc Le Chevalier at American Water and all have done some really interesting work in tracking what causes these negative transients and the importance of them. And that was just out of this, just solving a practical problem, some really interesting research got done, and it's led to further research. Then after that, I got to go back to Pennsylvania and work as an executive director of the Regional Sewer Authority. And it was like the best job I ever had and the worst job I ever had. I was in charge of a whole sewer utility and had huge budgets and controlled a whole large staff. And we turned around one of the worst run sewer authorities and made it an award winner in about 3 years. And it was a really good experience technically, but it made me realize I wasn't cut out to be an executive. I mean, I had to deal with unions and regulators and the media and the public, and worst of all, politicians. And I realized I really wanted to get into the technical side of things, and that was just about to drive me crazy dealing with all those different groups. So I decided I didn't want to be a boss anymore. Unfortunately, Wilkes University came along, and they were looking for an environmental engineering professor, and so I was able to escape from the best job I ever had in a way.
So your training, your PhD training at Vanderbilt didn't prepare you for dealing with unions and administrative work?
No, it was, and just my personality also. I would put in huge hours worrying and agonizing over every little detail, and you can't do that in that kind of position. You've got to delegate, and there's just the people issues were kind of crazy.
In the late 1980s, we were both on a AWWA Computer Advances Research Committee. And you wrote a paper on the future of water distribution modeling, and I think the title was something, What Modeling is Going to Be Like in the Next 5 Years. And one of those topics that you talked about was real-time modeling, an area that is just now maturing 25 years after you discussed this concept in your paper. Has the water distribution system analysis field progressed along the lines that you predicted a quarter of a century ago?
Yes, but a lot slower. At least in this area, things are looking like they are going to really get a lot better, as opposed to some of my things about optimization. I mean, there's fundamentally a lot of value in having models not just be a tool for engineering and design, but also a tool for operations. And there have been uses throughout the years. Even when I was in Austin, we did some interaction with the operations people. But now it's really getting more and more of a thing that modeling should cut across the whole utility. And it's slow to catch on because control room operators are a different breed of people. They don't want a computer program telling them what to do. And so it's a very slow process, winning their trust and getting them involved and getting them to realize the value of it. Now, because operating a system is mostly boredom, and there's a small period of almost panic and terror when something goes really wrong. And models are especially useful if you have an up-to-date model of helping you analyze those problems when things don't go right. During normal operation, the role of modeling is more trying to minimize energy use and doing that sort of thing. But it's during the emergencies that the modeling really has a lot of advantage to help you in decision support. And we're finally seeing that, and we're finally trying to do a much better job. We spent a lot of time over the last couple of years trying to have the models integrate better with system operations. And we have made a lot of progress, but there's still hurdles ahead of us. But it's, when I first met John Hasted, one of the first things we talked about was you need to get this stuff beyond the engineers and into the operations. And, like I said, 25 years later, we're finally doing it. So I guess the idea is his time has come now.
Yeah, more on John Hasted later. You mentioned that in 1992 you went to Wilkes University as an associate professor. How was your experiences in academia? You've been very vocal in recent years on the need for close cooperation between academia and the practicing engineering field to ensure that academic research is relevant to the needs of the engineer and that practicing engineers are aware of the advances coming out of academia. Can you elaborate on this?
Okay, there's two questions in there now, Walter. The first one was about my experience at Wilkes, and that was great. It was sort of like a 5-year vacation, looking back at it, where I was able to just have fun teaching the students and had a great time there. And I could have stayed there forever, I guess, if I wanted to, but decided to get back into practice after a couple of years. But we went for a program that wasn't ABET accredited and made it accredited, and it was really fun building an environmental engineering program with essentially no money. I mean, some of our early lab equipment we built with plexiglass sheets and duct tape and baling wire, and gradually over the years the program has really grown and become quite successful. But we really started out with almost nothing except some really enthusiastic students who were really wonderful.
Yeah. The reason I grouped those two is I think since you did serve in academia for a number of years, I think you're better able to answer the second part of that question.
Okay. Well, no, but this was a different academia, because this was a bachelor's degree program where the emphasis there was teaching, which I loved. It was not getting grants. And that's unfortunately, when I look at a lot of what goes on in the big research institutions, it's not so much about teaching. I don't think I would have enjoyed myself as much if I went to a major research university where to me, it looks like from a distance, and maybe this is unfair, that getting grants is number one. I remember talking to a very well-respected guy in our field, and his statement was, he gets rewarded for bringing in money and publishing papers. And if somebody happens to find that useful, well, that's wonderful, but his job wasn't to publish useful papers. It was to bring in grants. That's how he got promotion and tenure and such. And that's kind of scary that's the way the system seems to work.
You've been affiliated with Hasted Methods and later Bentley Systems since 1990s, initially as a consultant and teacher, and since 2000 as an employee. So it's now been 15 years in one place, which is a long time for you. Can you tell us about the early years at Hasted Methods and its founder, John Hasted?
Yes, John Hasted is still kind of an interesting character who was really good at seeing needs and meeting them. And he was great at selling stuff. That was the thing, and he knew to hire good people and let them work and develop some really good software. It was always exciting working with John. He would, one day you'd be heading south 100 miles an hour, and the next day you're going north 100 miles an hour, because he would, a phone call from an upset user would, make him very upset, and he would say, okay, we've got to solve this problem right now. Sort of like when 9/11 happened. A lot of people talked about how there should be some kind of response, and John said, we're going to do something about it, and he organized a conference. Everybody dropped everything, and we organized a conference just a couple of months after 9/11 about water security. And he brought in people from all over the world to speak. He basically, and he charged $0 for people to come to attend the conference. While other agencies took several years eventually to come up with programs about water security, he did it. And it was just that attitude of his of, all hands on deck. We have a problem, we're going to solve it. And it was a lot of times crazy, but he had brought a lot of enthusiasm, and he let the workers get their job done. And you knew where you stood with him. Like now, most places I've been in have been in a large bureaucracy, and with John there was no bureaucracy. It was basically a flat organization. You'd go up to John and you'd say, "This is what I want to do, John," and he's tell you either you were crazy or why aren't you done with it yet? I mean, it was just, you had a decision immediately, unlike most other organizations I've worked with, like the Corps of Engineers or such.
It's a little difficult question, but answer it or don't as you feel. Software developers and vendors are primarily, they're in there to make money, for a company, and then that makes sense. And sometimes they'll make decisions to develop a piece of software or not based on whether they think it's going to have sufficient customers. Are software developers in the field of water distributions, are they being responsive? Are they developing the products that we need for tomorrow?
I certainly hope so, because that's a major component of my job right now, is those meetings we have to decide what are we going to do next. Okay, so we'll ship a release of a product, and then it's okay, the next day you get done patting yourself on the back and you're deciding what's our next hurdle we're going to go over. And there's a lot of heated discussion that goes on, and lengthy discussion about where our priorities are. And fortunately with Bentley, they allow us a good deal of latitude to decide our own direction. There are some things that get pushed down from the top, but for the most part, our team can decide what we think is the most important, and sometimes they even listen to me. Sometimes, there's a group of us that get together and decide where the priorities lie, and I have some say in that, but it's really a group decision by the team as to where the next priorities lie, and we very much listen to what users are asking for, but also we keep an eye towards what can we do that's really beyond what they're asking for, to make it not just what they think they want, but what will be the next big thing. And it's a continuing competition, and the fact that we do have competition makes it really interesting to try to see who's going to leapfrog who and have the best products.
Most of your work has emphasized practical use of models. And I think that's reflected in the books and papers that you've written, starting with in terms of books. You wrote a book back in the early 1980s. You were lead author on the very popular book that Bentley Systems, Hasted put out and then Bentley put out. Can you talk about what your philosophy is in terms of both papers and books?
Right. When I wrote Analysis of Water Distribution Systems back in '83, it came out in '84, the preface had something in the start along the lines of, I wish someone had written this book before me so I wouldn't have to write this thing. Because up to that point, there were a lot of journal papers out. There was one excellent book by Roland Jeppesen about how to solve the equations, but there's no real book out there about how to do modeling from a practical standpoint. And I looked all over for it. There would be a little paper here or there, but there was no really comprehensive, practice-oriented book. And so I figured, I've written papers here and there. Let's tie it all together into a book. And it, I think, addressed a need. I think at the time, it really was that first book that I would have wished someone had written, so they just handed to me, say, here, Tom, read this and start modeling. And I laid out some ideas that I think I still support nowadays. So that was I think an important thing in my career, and I think it helped the state of the art in distribution system modeling. And it opened doors for me too. That's how I got a call from Austin. A fellow who I had dinner with the other night saw the book and said, "Hey, we got to hire this guy." And they gave me a phone call one day and said, "Hey, you want to come to work for us?" And so, a lot of times, in most of the jobs that I've been through, Walter alluded to the fact that I have had a number of jobs. I have not gone out looking for those jobs. People have seen something I've done and have asked me to apply for them. And so it's been that kind of a thing where if you're unhappy with your job and you hate what you're doing, you're probably going to be stuck with that job. If you love your job and you're enthusiastic, people are going to try to hire you away. And that's been my philosophy. And I've really had a good time in all my jobs. I've never had a really bad job. And that's kind of a good thing. Everything has been fun and challenging. Some a little too challenging, but I've been really lucky in having really good bosses along the way. It's really good to have people who trust you and give you enough leeway to do your job. And from the Corps of Engineers, I had Ray Montgomery, and Austin was Craig Bell. The board members, the sanitary authority, even though they were kind of crazy politicians to some extent, they supported me while I was going through the work. Wilkes, our chairman, Dale Bruns, was an excellent guy. American Water, Steve Seidel, our vice president, excellent. And the people at Haystead and Bentley later on, Bob Mankowski at Bentley now, are just outstanding people who supported me and let me do my thing.
We talked earlier about, in the area of practical applications, we talked a lot about calibration models. Some of the other practical problems or issues you've worked on are reliability of water systems, design, modeling, and operation of pumps, analysis of model results, and pipe break analysis. Though I'm sure you could write a book on these topics, and actually you have. Can you briefly provide your comments on how you first got involved in these areas and your assessment of whether the profession is on the right track in these areas? And I'm sorry, that was a multi-part question, but
yeah, we got about 2 hours here. Now, there's a number of topics that we could get into. Pipe break analysis, for example, really was triggered. We were doing some work, technical assistance to local governments from the Corps, and I read a paper by Shamir and Howard on applying present worth analysis to trying to decide when to replace pipes. And they did an excellent paper, but there was no real data on it. So I had a chance to do a study in Binghamton, New York, and Tony Policia and I basically took that methodology, tried to apply it to the real world, had to make some changes, of course, as you get to real world stuff. And people are still studying that paper that we did on analysis of pipe breaks and main replacement. I've done a few others afterwards with Jim Mayle and other folks. And we did a large study in New York City on pipe breaks, and we sort of did GIS before there was GIS. Where nowadays you'd have a GIS overlays of pipe breaks on top of schematics. In those days, what you did was you had a map of the city, a street map, and you put a plastic mylar overlay on top of it, and you had little sticky things that you put on top of the map wherever you had a pipe break, and you stand back and you look at that sort of thing. It was GIS before there was GIS, and it led to what was then called AM and FM for automated mapping facility management, which evolved into a lot of what we do in GIS today. But we sort of were doing that before. And Walter, you did a lot of work in precursors to GIS when your ADAPT work and all. And it's kind of neat to see all that stuff now just part of practice. So that was just one example, and I've got a bunch more if we want to talk about them.
How about pumps and pump operation?
Yeah, there's money to be saved. My saying on that is whenever you walk into a pump station, it's like walking into a gold mine. There's little nuggets of gold laying around on the floor of the pump station, and you just got to find them. And unfortunately, a pump doesn't say, hey, look at me, I'm running inefficiently. You've got to go and look for them, but you can almost always find ways to save money in pumping. And most of the time those savings, though, are due to pump testing, looking for mechanical wear and such. And one of the less important parts of that is pump scheduling. Yet if you look at the research literature, almost all the papers on pump operation have to do with pump scheduling, because that's kind of something that's kind of a neat research topic. And I wrote out recently something about a 10-step program to study energy management at pumping stations, and pump scheduling didn't show up until step 9 of that process, because there's so many other things that are ways where you could save a lot more money with a lot less effort.
Another area where you've done work and I think had a lot of interest is the reliability of water systems. Can you talk about that?
Okay, yes, because that gets back to the question about multi-objective design of systems. It's not just enough to have the system work when everything is operational, but what happens when things have to get shut down for pipe breaks or just routine maintenance or pump outages? How does the system work in that case? And that's really where reliability comes into play. Now, the impact of some type of maintenance event where you have to do shutdowns is you need to isolate the problem area. And you do that by closing valves. And it's amazing that so little of the work in optimization and automated design is around valves. There have been a lot of papers, but not much of it has gotten into practice. And so that's one of the things that we have worked on in our criticality features, is trying to identify distribution system segments, because when you think of distribution system segments, the logical way to look at it is edges and nodes, and that's the way hydraulic calculations are done, and it makes very good sense. But when you apply that to reliability, that doesn't really fit, because when you have a pipe break, one of the things that you do not do is eliminate an edge. You eliminate a part of an edge, or an edge and the node at the end of it and part of the next adjacent edge. I mean, valves are located on the edges. They're not located at the junctions. And so removing an edge is not an accurate way to model things. And there are a lot of surprises when you start to include valves in your distribution system design. You'll find, for example, that a pipe was laid in a semi-rural area where they went a half a mile without any valves. And over the last decade, they put in a school and a shopping center and a new subdivision. And all of a sudden now, one pipe break on that stretch of pipe can put out thousands of people. And people say, no, we would never do something like that in our system. Yet you go into every system, and there's places where a lack of valves has a real impact on the reliability and your ability to shut down and isolate a problem. And I've been, arguing in favor of that for a long time. I wrote the first paper about segments and the need to include valves, like in about '93 it was published. And we still have people who are trying to analyze reliability by just using that node edge topology approach.
You've mentioned several people you've worked with, or any other shout outs you want to give? Some of the people, I think you've probably done papers with a very large segment of our profession.
Oh yeah, this profession has just wonderful people all through it, and it's been a real joy to work with all these different people. I mean, you, Walter, Linda Ormsby, our friends over in Europe, guys like Orazio Guistalizi and Enrico Criaco from Italy, Dragan Savic and his group over in the UK. Some great work comes out of like Joby Boxhall over in the UK and Bogumila Ulinicki. Then of course the Australians with Angus Simpson and Martin Lambert and those guys. There's just a large group of really wonderful people that I've had the opportunity to work with over the years, and I apologize for those of you that I've left off who are maybe watching to say, why didn't he mention me? But there's been some really good people, and those people I've mentioned are mostly the people who are publishing and doing research, but there's also a whole array of folks out there who do some great work and who never publish an article. The folks at American Water, like John Young, Gary Naumick, Jim Chelius, Jen Yang, that are the modelers for American Water, which is the largest, investor-owned utility in the United States. There's some really wonderful people there. In Aqua America, there's some really good people like Frank Grablitz and Joe Thurwanger. They're the real modelers that are doing this work. And every consulting company has some really good people. There's guys like Earl Schneider and Sasha Tomic, and there's so many, Kevin Laptos, that I've worked with over the years. There's some really great people out there in the industry, and it's really a lot of fun to work with those guys. Don Chase, I've got to mention him as well. And it's look forward to working with them going forward.
Any other thoughts you'd like to share with us? Maybe talk a little bit about what you see the future of water distribution modeling?
Well, what I'm afraid of the future is that the researchers are going to go this way and the practitioners are going to go further that way. Remember when at the 1985 session there, I was talking about, I had a slide showing the researchers were on one side of a gap and the practitioners on the other side. And Uri Shamir got up and says, well, your gap isn't big enough, it's really wider. And it seems to have gotten even wider yet over the years. And one of the things that I do is encourage people to talk to folks in the other side of that gap. If you're a researcher, talk to the people who work in the local water utility and see what they're working on and listen to what their problems are. And similarly, if you're with an engineering company or utility, talk to the professors at the local university. They have some great ideas. And if we get these people to talk together and work together, there's just so much more that we can do by collaboration like this and having folks work together. It's really a great way to go. And also Uri and Avi over in Israel, I want to make sure I don't forget about them when I'm thinking about names of people I should have mentioned along the way.
Well, Tom, thank you very much. It's been a very enjoyable experience.
Okay, well, thanks for inviting me, Walter. Good questions there.